Hey, welcome back to Math with Patrick. Today's May 18th, and we're solving problem number 138 from this Daily Epsilon calendar. And we need to figure out why this fraction here, something divided by something, is equal to 18 today. And it says, let sigma naught of n, not the word not, like N-O-T, not, but like N-A-U-G-H-T, like nothing not. So let sigma naught of n be defined as equal to the number of divisors of n. I have seen it sometimes just written as like d of n, where d kind of just stands for divisors. So if I did like d of 8, I think that'd be 4, because like 1, 2, 4, and 8 can all divide the number 8 evenly. Maybe if I did like a prime like 7, then there would be exactly 2 divisors, because for any prime number, the factors or divisors, whatever you want to call them, of any prime is just going to be 1 and itself. So I guess let's just use the notation from the calendar today and use sigma naught. And I can say sigma naught of 7 is equal to 2. It'll be a little bit harder with this factorial here. And there's kind of 2 ways to approach this. The first way is to figure out what this number is. Let's do that right now. A factorial is just like a product of your starting number, 6 in this case, and all of the natural numbers down to 1. So 6 factorial is going to be 6 times 5 times 4 times 3 times 2 times 1. And this number just turns out to be 720. And so one way to figure out how many divisors there are of a number is just to write them all out. You can see in this list on the right there, I start with 1 times 720, and I'm just incrementing this number up to the next one, the next biggest number that would also evenly divide 720. And so like a lot of just our counting numbers are going to work, but I'm going to skip 7. And maybe you would expect this because I don't have like this times 7 anywhere in 6 factorial. And so that's going to be the first number that I skip. There's going to be a few others like, 14 is missing. Again, kind of no 7. 13 is missing. That's prime. I don't have any 13s in here. So it is possible to figure out how many divisors there are of a number by just writing them all out and counting them. And I think there's 30 here, right? We can see that there's 10, 10, and 10 more. So there are 30. But I don't really want to do this for 11 factorial. That's going to be a lot bigger. And I really don't want to write them all out like that. So I want to make a strategy for like finding out this 30 without needing to write out all the factors. And I think what we can do is pick apart this number and learn about its prime factorization. And then there's a strategy in there that helps you count the number of factors of a number. So we can split up this 6 into a 2 and a 3, and this 4 into a 2 and 2. And so 6 factorial is the same as 5 times, looks like I have 2 3s, so 3 squared. And I have 1, 2, 3, 4 2s, so 2 to the power 4. I guess I'll put this times 1 at the end. Why not? It doesn't really do anything. And so this number that I just wrote is the same as 6 factorial. It's the same as 720. And if I wanted to create a divisor for this number, I should grab some amount of 5s, some amount of 3s, and some amount of 2s. I could either grab no 5s or one of them. That's all the options I have. I could have 0, 1, or 2 3s. And then I could have 0, 1, 2, 3, or 4 2s. So if I take like no 5s, no 3s, and no 2s, I am just left with the number 1, and that is a divisor of 720. I could take everything, right? And this would produce 720. That divides itself as well. Any number that you can see in that list on the right, I can create uniquely by circling one of these 2 numbers, one of these 3 numbers, and one of these 5 numbers. Like say this 10 would be right here. 1, 5, 1, 2, and no 3s. And so I'm going to use the fundamental counting principle here, where if I have 2 options here, 3 options here, and 5 options here, I know that I can multiply these numbers to get the total number of options, which will be 6 times 5, which is just 30. And the 2 and the 3 and the 5, I'm getting that from basically just adding 1 to these exponents. I guess there's like this invisible exponent of 1 above the 5. And when I add 1 to that, that's where I'm getting this 2 from. And so if we use this process on 11 factorial, we could count the amount of divisors without actually needing to write out the whole list. So let's try it out. 11 factorial is going to be equal to 11 times 10 times 9 times 8, all the way down to 1. Then I can split up some of my composite numbers, like 10 is just 2 and 5, 9 is 3 and 3, 8 is like 3 2s, all wearing a trench coat. 7's prime, 6 is not, 2 times 3, and then 4 is going to be my last composite number. Let's see how many primes we have. We have just the 1 11. We have just the 1 7. I think we have 2 5s, right? We have 1 here and 1 here, so 5 squared. We have a bunch of 3s. There's 1, 2, 3, 4, so 3 to the power of 4. And a lot of 2s. There's 1, 2, 3, 4, 5, 6, 7, 8. Cool. All right, and if I trust the process from earlier, where I add 1 to all the exponents and multiply all those numbers, then I should get the number of divisors for 11 factorial without needing to list them all. So let's try that out. It's going to be 2 times 2 times 3 times 5 times 9. There we go. So I'll write sigma naught of 11 factorial is going to be equal to this product. Well, 2 times 2 is 4, times 3 is 12, times 5 is 60. And you know what? I'll actually just keep it as 60 times 9, because when I do this divided by that, that's going to be 60 times 9 over 30. And then I can see how the 60 and the 30 could simplify to a 2 and a 1. And then 2 times 9 is just 18. Cool. So we have 18 as a fraction, and that's today's date. So there we go. Just a little bit of stuff about this divisor counting function. And looks like we got 18. So I'm all done. Thanks for solving this with me. And I'll see you tomorrow. All right. Bye-bye.